Good afternoon and welcome back again. So, we will continue our lecture series, and if you are keeping count, this will be the 9th lecture, and I am going to quickly just put down a title for the talk, and then we will go on to recap what we did in the last lecture. So, I am going to call this lecture the dual code. Okay. And let us take a quick recap of what we did in the last lecture. So, in the last lecture we looked at the notion of spanning, the space spanned by a set of vectors. We looked at an example. We looked at an example of a standard, the standard basis and the space spanned by it. So, we introduced, so the standard basis is an example of a basis, of course, and basis is defined as something that combines the concepts of linear independence and spanning. We defined that, we looked at examples, then we actually stated a theorem which said that supposing you have a vector space that contains a finite number of elements in its basis, then we showed that that number will be the same across different bases for the same vector space. And by counting the number of elements in that basis, you get the notion of dimension. And after that, we defined what it means to talk about the dimension of a code, and we looked at some notation, and that I think is about where we stopped. So, today the plan is to actually continue and develop the notion of linearity a little bit further. So, we will introduce along with the code a notion of another code that is strongly associated to the original code and is called the dual code. Okay. So, let us just let me first begin with a quick overview of our last time's lecture. Now, this is small for you to view, but hopefully by the time you are seeing this you will have a hard copy in your hands. So, it should not be hard. Right. So, here is where we finished the discussion on spanning, then we talked about a basis. We proved that a basis contains the same number of elements. We talked about the dimension of a vector space, applied it to a code, defined what is meant by dimension of a linear code, and we defined some notation in connection with it, and took a quick look at an example. Okay. So, our recap, we will put down that we have concluded our discussion on spanning. And then we defined what it means to talk about a basis for a vector space, and here we looked at examples, and we also proved that roughly speaking any two bases for a given vector space contain the same number of elements. This led to the concept of dimension. First, of a vector space, and then of a linear code. And then we looked towards the end at examples. So, this example is an example of a basis for the single parity check code, which allows us to assign a dimension of 6 to the code. So, I just want to reiterate a couple of points as I begin the lecture. So, we will just call them out as notes. Note: a given vector space can have more than one basis. For example, if you look at R3, then you have the standard basis which we looked at last time. But we also pointed out that any 3 vectors not on a plane also form a basis. So, which goes to suggest that a basis is far from being unique. On the other hand, there is a property of a basis. So, we are making note. So, this was our first note. So, let me write A and put a circle around it. And the second note is that given a basis alpha 1, alpha 2, alpha n for a vector space. Actually, let me make this a little bit more general. I will allow the vector space to have an infinite basis. So, given a basis alpha 1, alpha 2 dot 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 for a vector space V, every vector has a unique expansion as a linear combination combination of elements of the basis. And okay, so the key point is it has a unique expansion and also as a linear combination. So, the proof is straightforward. Suppose now supposing you have a vector x which on the one hand is sigma C I j alpha I j, j is equal to 1 to r, and it is also given by, let us say, k is equal to 1 to s, c a I k alpha I k. Okay. But this would imply that the sum j is equal to 1 to r, c I j alpha I j minus the sum k is equal to 1 to s a I k alpha I k is equal to 0. But by the linear independence of the alpha I, it follows that this can happen if and only if r is equal to s, the alpha I j are the same let me just make one change here. I see that there is a possibility of confusion here. I want to change the I sub k's to L sub k, so that we leave open the possibility that the vectors on this side are different from those on the right side. So, sorry about that, let me just quickly make that correction. So, here this is L k, L k, L k, L k. Okay. So, I have made this so that these sets of vectors could ostensibly in the beginning at outset could be different, but the only way this can happen is if all the coefficients in front of every alpha are 0, right, and that can only happen if and only if r is equal to s and alpha I j and alpha and the alpha L k are the same. You have the same set and the coefficients are the same. Okay. So, what that proves is that every vector has a unique expansion with respect to a basis. Let us take a quick example. Supposing you are in 3-dimensional space and you are looking at the vector 1, 2, 4, let us say, then we know that there is only one way, and let us say that your basis is the standard basis. which is that alpha 1 is 1 0 0, alpha 2 is 0 1 0, alpha 3 is 0 0 1. Okay, so this is your basis. Then it is clear that x is 1 times 1 0 0 is 1 times 1 0 0 plus 2 times 0 1 0 plus 4 times 0 0 1, and that this is the only way of writing it. So, our point is that these coefficients are unique. This coefficient set is unique, right. Now, okay, so we have made two remarks concerning a basis. So, now let us look at a basis for our example codes. For the three example codes, example 1, the repetition code. So, in this case it is easy to see that a basis has just a single element, namely the all 1 code. So, this is a singleton basis. Example 2, if you look at the single parity check code, then a basis for this is now we have actually looked at that before. So, let me take advantage of the technology that we have to bring that up. Okay. And I am going to paste that over here. Okay. So, this is a basis for the example parity check code. So, let me the collection of 6 vectors below. I am not providing too much by way of justification, because I think it is fairly straightforward. It is clear that they span the space and these vectors are linearly independent. So, they meet the criterion. So, it is fairly clear that they are a basis. The last example, the Hamming code, perhaps needs a little bit more of work. So, example 3, the Hamming code. Now, so let us begin with our 3 circles diagram. And the symbols are M0, M1, M2, M3, and you have the parity check symbols P4, P5 and P6, right. So, this is the code and I am going to write the code words in a certain fashion, which we will encounter again in just a little bit. So, I am going to write the entire code word like this: M0, M1, M2, M3, P4, P5, P6. So, this is a row vector which I am going to express in matrix form okay. And let me draw some lines to help keep me organized here. So, this is 3, and so this is 0, 1, 2, 3, 4, 5 and 6. And I am going to, what I am going to do here is, my goal is to actually fill up this matrix, keeping in mind that the vector that I would like to generate is this vector, and so let us see how we do that. Okay. So, my goal is to actually generate this code word over here, and I want to express it in terms of the MIs. I am going to think of the MI as message symbols, and I am going to fill in this matrix accordingly. So, from that it is not too hard to see that the correct way to fill it up is like this. Now, at this point I have expressed the first few symbols. Now, I need to look at how to generate P4. P4 is a linear combination of M0, M1 and M2. So, what I do here is I put down 1, 1, 1 and a 0, and in a similar fashion to generate P5, it is M0, M2 and M3. So, that is 1, 0, 1, 1, and for the last symbol it is M0, M1 and M3. So, I have written down an expression which tells you how the code words in a Hamming code are generated, but this particular matrix is a matrix that we will frequently encounter. It is called a generator matrix, but before we get to that, let us just notice a couple of features of this matrix. Excuse me. So, first of all, getting down to the matrix, you can see that every code word can be expressed as a linear combination of the rows of this matrix. So, I am going to call this matrix G. Okay. We call this our matrix G, and this stands this is short for generator matrix. So, every code word can be expressed as a linear combination of the rows of this matrix. So, it certainly is true that the rows span the code, and it is also clear that they are linearly independent. Hence, the rows of this matrix form a basis for the Hamming code. Okay, so, that is the conclusion. The rows of G form a basis for the Hamming code. Okay. With that, we are now ready to move on to the main topic of this lecture, which is the dual code. So, definition: let C be an NK code. If you will recall from the last lecture, we explained that this is notation for a code, for a linear code whose block length is n and whose dimension is k. The dual C perp of C is defined by C perp is equal to the set of all vectors y such that x transpose y is equal to 0 for all x in the code. Okay, it is important that this is for all. So, this is what is meant by the dual of the code. Let us do a quick example. If C is the repetition code, that is, C consists of the vectors okay. Recall that the dual code is the set of all vectors which are such that when you take the inner product with either of these code words, you will get 0. So, certainly you will always get 0 if you take the inner product with 0. So, the only requirement is that the inner product with the all one vector is 0, which is equivalent to saying that the vector has even parity. Okay. So, from this it follows that the dual of this code is nothing but the single parity check code. So, we will note that clearly. The dual of this code is the single parity check code. All right. And so, we can summarize this and say, i.e., if you take the repetition code, its dual is the single parity check code. So, an interesting question that you might ask is, what is the dual of the single parity check code? So, we will put that down as a question. What is the dual of the single parity check code? Or in other words, i.e., what is the dual of the dual of the repetition code? Now, some of you may actually guess the answer. The answer turns out to be that C dual is C always, not just in this instance, that is always the case. So, our next goal is to actually prove this. So, but along the way to providing a proof for this, remember just a few minutes ago we introduced a generator matrix for the Hamming code. So, what we will actually do is we will define a matrix G associated to every code. So, definition, let C be an NK code, then any K by N matrix whose rows form a basis for C is called a generator matrix. Now, an obvious comment, because remember when we were talking about a basis, I mentioned to you that given a vector space, a basis for the vector space is not unique, you can have several, and it follows therefore that given a linear code, there could be several bases, several generator matrices for the code. So, note every code can in general, or rather not every code, let us say a code, more exactly, more precisely, a code can in general have more than one generator matrix. Right. Now, as far as examples go, we have already seen a generator matrix for the Hamming code. Okay. So, in retrospect, since this is in retrospect, perhaps I should use a different color. Let me write in green. Yeah. So, I will put down here this is a generator matrix for the Hamming code. Okay. So, example 1. One, the Hamming code so the example was provided earlier. Example 2, for the repetition code, it is not hard to see that the generator matrix is very simply a row of all ones. Okay. And now, one remark here is in order. Now, when I talk about the repetition code here and I put down vectors, I am putting them down as column vectors. However, when you view them in terms of the generator matrix, code words appear along the rows. Okay. So, you have to adjust for that, and it is standard terminology in coding theory to define generator matrices the way I have defined it. So, there for whatever historical reason it is the rows that appear as code words. Okay. But still my notation will be that by default a vector is a column vector. So, this is a basis for the generator matrix for the repetition code, and for the single parity check code case, a generator matrix is simply obtained by simply putting down in the form of rows the vectors that we had looked at earlier. So, let us see if I can pull that up. Yeah. So, these vectors which we have written down as column vectors, if you write them down as rows of a matrix, then you will obtain precisely a generator matrix for the code. Okay. So, that is what I am going to do. Okay, so, this is a generator matrix, and we will always use the symbol G to generate to denote a generator matrix. And notice that the matrix will always have, so since the single parity check code has parameters 7, 6, it is a 7, 6 code. So, this matrix is therefore 6 by 7. So, in general the generator matrix will always be a k by n matrix. Now, okay, so what we have done up to now is we have introduced the generator matrix. I mean, we first introduced the null code, the dual code, and then I introduce the generator matrix. So, next what we will do is we will make a connection between the two. So, I will put that down as a theorem, perhaps as a lemma. The null space of a generator matrix for the code C is precisely the dual code. So, how do you prove that? So, proof now so let x be in the null space of G. Okay. So, perhaps it is worth making a note for those who are not familiar with the terminology of a null space. Note the null space of an M by n matrix A is precisely the set so, I am going to write script n A to denote the null space is the set of all vectors x such that A times x is 0. Okay. So, this is notation for the null space. So, we want to prove that the null space of the generator matrix is precisely the dual code. So, let us x be in the null space of G. Okay. Therefore, it follows that G1 transpose G2 transpose GK transpose times the vector x is 0. So, that means that the inner product of the vector x with each of the rows of the generator matrix is 0, okay, if something is in null space. Now, if you think about the rows of the generator matrix, so let me write down G just to remind you that this is our generator matrix. The rows of the generator matrix are a basis for the set of all code words. So, if anything is in the dual code, it must have inner product 0 with every one of the elements of the basis. So, in other words, if anything in the dual code must lie in the null space. Okay. So, that much is clear clearly by definition of the dual code. So, let us make a note of that. Clearly from the definition of of the dual code, it follows that if y belongs to the dual code, then y belongs to the null space of G. So, that much is clear. On the other hand, if something belongs to the null space, then its inner product with every one of these rows is 0, and from that it is easy to see that its inner product with any linear combination of the rows is 0, and therefore, it belongs to the dual code. Okay, so, we will put that down in writing. On the other hand, if X belongs to the null space of G, then X transpose G I is equal to 0. If C is a code word, then C can be written as sigma mi G I is equal to 1 to k. Now, therefore, X transpose C is equal to X transpose sigma I mi G I, which is sigma I mi X transpose G I, and we know this to be 0. So, this entire thing is 0, which shows that X belongs to the dual code. So, okay, this is just by linearity. If the inner product of X is 0 with every row of the generator matrix, it follows that its inner product is 0 with every code word. So, what that proves is that if X is in the null space, it belongs to the dual code, and earlier we showed that if something belongs to the dual code, it belongs to the null space. So, that proves the theorem. Okay. All right. Now, we are ready to introduce a second matrix. So, I will term this section the parity check matrix. Definition: the parity check matrix, or excuse me, let us say a parity check matrix, because again there can be many. A parity check matrix for a linear code C is any, and we will give this a name. So, we will write H is any generator matrix for the dual code CPUP. So, now the first thing that must strike you is that, well, if I want a matrix that is connected to the code C, why is it that I have to go to the dual code? Okay. But I think that will become clear from an example. So, supposing we look at, let C be the single parity check code. The dual code C perp is the repetition code. Is the repetition code having generator matrix H, which is 1 1 1 1 1 1 1, and we have already seen that. Okay. Now, note one thing, I am calling this the matrix H because although it is the generator matrix for the dual code, our focus is on the original code, and we have already reserved the symbol H to denote the generator matrix for the dual code. Okay. So, that is the reason for calling it H. Now, still what I am trying to explain through this example is why is it that this matrix is called a parity check matrix for this code. Now, the key point is that the code in relation to this matrix, the code appears as the null space of this matrix. Okay. So, let us make a note of that. Note that C belongs to the code if and only if H times C is equal to 0, which is another way of saying that sigma C I is equal to 1 is equal to 0. Okay. So, what this matrix is actually doing is it is laying down the parity check condition satisfied by all the code words in the single parity check code. Okay. So, this is precisely the parity check, the parity condition satisfied by code words in C, hence the name. Okay. So, this is the reason for calling H the parity check matrix of the code. Now, what we would like to show next is that so I am not sure if we are going to have enough time to finish, but let us give it a try today. So, theorem C dual is C, that is the dual of the dual is the original code. Okay. So, note that C. So, I think that perhaps this theorem is best postponed until the next lecture, at least the writing down of it. So, let me just go over the arguments. We want to show that the dual of the dual gets you back to the code. So, so rather than calling this the proof, let me just call this a sketch of the proof. Okay. So, this we will just I will formally put down the proof next time. The sketch is that, so let H be a generator matrix for CPUB. Okay. We know that the null space of H is the dual to the dual. Okay. So, the question really is this equal to the code? So, what we will show next time is that by making an argument with regard to dimension, which is essentially a counting argument, we will actually show that the two are the same, which will establish that the dual of the dual is the original code itself. Okay. Once we have done that, then we will look at means of actually finding the generator matrix of a code is easy enough to find. So, we look at how to find parity check matrices. Okay. So, I think this is a good place to stop. Thank you.